All right, well, now we're going to start on chapter 13. And chapter 13 is all about solutions. So we'll go ahead and go to the first thing here. So whenever we make a solution, over here on the left, we've got some salt that we're dissolving in water. And we want to determine what things are happening when one thing dissolves in another. And so whenever a solution forms, we'll find that the particles are evenly distributed, that they are dispersed evenly throughout the mixture, throughout the water. And we'll find that there are two major factors that will help us to determine whether this process can occur. And those two factors are going to be entropy and intermolecular forces. So we'll look at these in a lot more detail as we go through this. So to help us get started, we're going to kind of skip ahead to an equation that we're going to see in chapter 19. This equation, delta G equals delta H minus T delta S. Now, two of these things you've already seen before, and that is delta H, of course, is enthalpy, and T, of course, is temperature. But the things that you haven't seen are the Gibbs free energy, and this is a new topic for you guys. We're going to talk about it, like I said, in great detail in chapter 19. However, right now we'll just say that we'll just say it's an important thermodynamic quantity that helps us to determine, can something happen? All right, as far as delta H is concerned, delta H is the enthalpy, and as you probably recall from the first semester of chemistry, enthalpy is the amount of heat that is either given off or absorbed in a reaction. And again, we'll talk about that in more detail. If enthalpy is positive, if delta H is positive, that means the reaction was endothermic. And if delta H was negative, that means the reaction was exothermic. T is the temperature. That temperature does have to be in Kelvin. And then delta S is the entropy, and or the change in entropy. And entropy, we're going to dig into that a little bit more. I want to dispel a couple of misconceptions about entropy, so we'll get to that. So what we're going to learn in chapter 19 is if a reaction or process has a delta G that is negative, then that process is going to be spontaneous. So if we put all the factors in here, we put the numbers in there, and we come up with a delta G that's negative, that means that process can occur. It doesn't necessarily mean it will occur, but it means that it can occur. All right, so what this means, well, we're going to find that the delta H is going to be determined by the changes in the intermolecular forces. Those changes in the intermolecular forces are well, we're going to look at those in a little more detail here in a minute, but those things will determine how much heat is either given off or absorbed over the course of the reaction. Delta S is going to be determined by the distribution of energy in the system. And we'll get to that in a little bit more detail here. This really won't make 100% sense until we get to chapter 19, but I'm going to give you at least a little bit of an idea of what it means for delta S to be either positive or negative. So as far as entropy, what I want you to understand about entropy right now is that when a gas or a substance spreads out, we will find that the entropy will increase. So for example, here we've got a pair of gases, each in their own chamber, oxygen on the left side, the argon over here on the right side. But let's imagine for a moment that I didn't have any argon here. And we have this partition. If we remove that partition, the oxygen will spread out to fill that container, just because gases will always expand to fill whatever container they're in. Likewise, if we had argon only on the right and no oxygen on the left, and then we remove the partition, then the argon would spread out to fill that container. Well, That means that if we have oxygen on the left and argon on the right, and we remove the partition, then the oxygen will spread out this way to the right, and the argon will spread out over to the left. And we will end up with a completely uniform mixtures. It turns out gases always do this. Gases will always spread out to fill whatever container is available, even if there's another gas that is there. So that means that this process is automatically spontaneous, and the reason that it is spontaneous is that the change in entropy is positive. So anytime a substance spreads out, the entropy, the delta S is going to be positive. So the entropy will increase. As far as our equation, the delta G equals delta H minus T delta S, the delta H is going to be essentially 0 because there are no intermolecular forces to really worry about. If you go back and look at chapter 10 talking about, and chapter 11, talking about how gases really don't have extensive intermolecular forces because the molecules rarely actually run into each other, or they're rarely in contact with each other. They run into each other all the time, but they're not in contact with each other for very long. All right, so what we want to do is we want to look at delta H. We want to look at delta H. Now that we have at least a little bit of an idea of what delta S is, anytime a solution is formed, delta S is going to be positive. So anytime a solution is formed, delta S will be positive. So what we want to do here is we want to look at the different types of intermolecular forces. And fortunately, you guys are quite familiar with these because we just did these in chapter 11. So we just did these in chapter 11. There's the dispersion forces. Remember, everything has dispersion forces, but those dispersion forces are more prominent in things that are nonpolar. The dipole-dipole interactions, you have to have something that's polar and something else that's polar. And if you have that, then that's going to be more prominent usually than the dispersion forces. Hydrogen bonding, well, remember the requirements for hydrogen bonding. It must have a hydrogen. That hydrogen needs to be covalently bonded to oxygen or nitrogen or fluorine. And there needs to be a lone pair of electrons on that nitrogen, oxygen, or fluorine. And then finally, ion-dipole interactions. To have that, you need to have an ion and a dipole. And ion-dipole interactions are usually quite strong. So what we want to do is we want to look at number 13 and determine what are going to be the most important intermolecular forces in these processes. So we're going to skip over here to the in-class assignment. So here we go. We've got our in-class assignment. We want to indicate the type of solute-solvent interaction that it should be the most important for each of these. All right, so for carbon tetrachloride is a nonpolar substance. If we look at the molecule, we've got the 4 chlorines around the carbon there. There's no lone pair on that central atom, and because there's no lone pair on the central atom, it's going to be nonpolar. For benzene, benzene's only got carbon-carbon and carbon-hydrogen bonds, and usually things with just those two elements are nonpolar. So we're going to find that's also nonpolar. So nonpolar, it's got to be dispersion forces. So we're just going to put dispersion forces are going to be the most important type of interaction. For this next one, we've got methanol and water, and you probably can tell without even drawing these what the interaction is going to be, but I'll go ahead and sketch this out. So there is methanol, and you see that it's got the lone pair electrons and the hydrogen, and of course you guys know what water looks like, the Lewis structure for it. Again, we've got the oxygen with the hydrogen on it. This is very clearly going to be hydrogen bonding. So hydrogen bonding will be our most important interaction on that. All right, for our next one, KBr and water. I'm not even going to draw this out. We already know what the water looks like. But for KBr, that's an ionic compound, and when it dissolves in water, the most important interaction there is going to be ion dipole. So ion dipole. And then finally, here we've got HCl and acetonitrile. Now this one's a little bit tricky. I'm going to go ahead and draw it real quick here. So HCl, I'm going to draw it backwards. So there's the chlorine with the hydrogen. And then, that is supposed to be a carbon. So carbon, and then here I'm just going to put CH3. We saw acetonitrile in chapter 11, and we saw that we've got a very polar bond here in between the carbon and the nitrogen. There's a triple bond there. All right, so with that carbon-nitrogen bond, it's very polar. This is very polar. So we definitely have a dipole-dipole interaction. What we want to ask is, does this count as hydrogen bonding? And the answer is not according to the book. However, if you ask some people, they would probably say this is a pretty strong hydrogen bond. We're going to go with the book definition. And the book definition requires that we have to have a hydrogen that is covalently bonded to either nitrogen, oxygen, or fluorine. And so chlorine doesn't quite cut it. So we're not going to count this as a hydrogen bonding interaction. We're simply going to call it a dipole-dipole interaction. All right. So now we're going to look at what actually happens when a solution forms. And whenever a solution forms, we're going to find that the solvent particles are going to completely surround the solute particles. We call this process of surrounding the particles with solvating. So it's called solvation, or the particles get solvated. So we want to we want to look at what's going on when we have, let's say, an ionic compound. So here we've got sodium chloride. Sodium chloride is surrounded by water molecules, and thus the water molecules start running into the sodium chloride, knocking off some of those ions. And when the ions get knocked off, you'll see that they get surrounded by water molecules. Well, that is called a solvated ion. And so here we have a chloride ion. You'll see that the negative charge on chloride is attracted to the partial positive charge on hydrogen, and that here we've got the positive charge on sodium is attracted to the partial negative charge on the oxygen. And this is just sort of in the process, and then eventually we will have all of these ions that are hydrated and in solution. All right, so whenever something dissolves, there's three interactions that we want to look at. And the three interactions, two of them are ones that we're giving up because we have to pull particles apart in order to make a solution. And one of the interactions is it's a new one, and that's what happens when the solute and solvent come together. So our first process is, we're going to call it delta H1. Delta H1 is going to be the amount of energy that it takes to separate the solute particles so that they're not in contact with each other anymore. Delta H2, and that's always going to be an endothermic process. Delta H2, also endothermic, it's making enough space in the solvent for the solute particles to be dissolved. And then delta H3 is the new interactions, the solute-solvent interactions, those new interactions that we get between the solute and the solvent. And so it's really quite simple. If delta H1 and delta H2 are bigger than delta H3, then we're going to get an endothermic process. If delta H1 and delta H2 are smaller than the magnitude of delta H3, we're going to get an exothermic process. All right. So here's what that looks like over here on the left. We've got the endothermic process where delta H1 and delta H2, I'm sorry, the exothermic process where delta H1 and delta H2 are smaller than the magnitude of delta H3. And so since that new interaction is stronger, we get an exothermic process. Conversely, if we look at delta H1 and delta H2, and it's bigger than the value of delta H3, then we're going to get a net endothermic process. Well, it turns out that both of these things can happen. Both of them definitely can happen. However, the one on the left is easier to do, and the one on the right is not as easy, but as long as we're dissolving something, then it's definitely possible to do it. All right. So normally at this point, I would do a demonstration where I mix some chemicals together, and one is endothermic and one is exothermic. And the whole reason I do that is to demonstrate that the enthalpy of solution can be both endothermic and exothermic, so that both are possible. But since we're doing this as a online class, then I won't be doing that. All right, so let's look at number 17. All right, so here's number 17 right there. When two nonpolar organic liquids such as hexane and heptane are mixed, the enthalpy change that occurs is generally quite small. So what we want to do is we want to use an energy diagram, that energy diagram that we just looked at, to explain why that happens. All right. Well, first of all, let's analyze what these chemicals are. We've got hexane, C6H14. Well, that is going to be a very nonpolar solvent. And then here we've got C7H16. That's also going to be a very nonpolar solvent. So nonpolar. The most important type of interaction for this is dispersion. For this is also dispersion, and the most important interaction between them is also going to be dispersion. That means that when we do this, that the delta H1 plus delta H2 is going to be approximately equal to delta H3, meaning that when we pull these particles apart, the interactions that we give up are going to be approximately equal to the interactions we get when we put the hexane with the heptane. So what this means is that delta H1 plus delta H2 is approximately equal to the negative of delta H3. Remember, delta H3 was usually exothermic, so if we take the negative of that, then that would give us the same value. In other words, delta H of solution is approximately 0. All right, so that is how we can explain that. Now, given that delta H of solution is approximately 0, we want to explain why hexane and heptane spontaneously form a mixture. Well, I'm going to write down this equation again. Delta G is equal to delta H minus T delta S. So delta G equals delta H minus T delta S. Well, when we do that, the delta H is approximately 0. For a reaction or process to be spontaneous, delta G needs to be negative. Since this is approximately 0, then the minus T delta S needs to be negative. Well, for minus T delta S to be negative, that means that delta S needs to be positive. Anytime you form a solution, particles are going to spread out. And when the particles spread out, delta S is going to be positive. So since delta S is greater than 0, the process will be spontaneous. All right, we're going to look at that in a lot more detail in chapter 19. We're going to talk about enthalpy in chapter 19. All right. Now, usually I showed this slide just to indicate that we want to distinguish between dissolving and reacting. Just because one thing appears to dissolve, that doesn't necessarily mean it just dissolves. When we're talking about one thing dissolving in another, really what we mean is that it's just looking at the intermolecular forces. When we get a reaction like this, which I'll go ahead and put that chemical reaction up on the screen. When we have nickel metal with hydrochloric acid, the hydrochloric acid, it does a single replacement reaction where we oxidize the nickel. Nickel's going from a 0 oxidation state to a +2 oxidation state over here on the right. And that hydrogen is going from a +1 oxidation state to a 0 oxidation state. So nickel is getting oxidized and hydrogen is getting reduced. Well, if we get changes in oxidation states, we're no longer talking about dissolution. We're talking about a chemical reaction, and that's different. The energy differences in chemical reactions are usually much bigger than they are with just dissolution processes. So even though I'm guilty of using the word dissolve, take a metal and dissolve it in acid, it's not really just dissolving. So just something to be aware of. Usually the trick that you can use to determine, one, if you look at the oxidation states, if the oxidation states change, then it is not just dissolution, it's an actual chemical reaction. The other thing you can do is if you dissolve it and you get this green stuff in solution and then you evaporate the liquid back off, then you'll end up getting something completely different than what you started with. Here we started with nickel metal, here we ended up with nickel chloride, and that's a very different compound. All right, so now what we want to do is we want to look at different kinds of solutions, and so we're going to look at what we refer to as saturated solutions versus unsaturated solutions. Saturated solutions are solutions that have as much solute as possible at that temperature. Now we'll talk about the temperature stuff here in a little bit, but it's got as much solvent as it can hold at that particular temperature. All right. What we'll find is that we will have some of the solute that is dissolved, but we'll also have some solid that's remaining in the beaker. So one of the key characteristics of a saturated solution is that we see some solid left over. So we'll see solid left over. So we'll have some things in solution and some things that are not. Now, you'll notice here it uses the word dynamic equilibrium, which means that there are constantly particles of this sodium chloride that are coming off and going into solution, and that there are also constantly particles of the sodium ions and chloride ions that are getting redeposited back onto the crystal. So the process doesn't stop just because you've reached equilibrium. It just means that the process will continuously go on forever. So that's what we mean by the dynamic equilibrium. So again, the key characteristic of a saturated solution is that there's some solid left over. For an unsaturated solution, the key characteristic is that there is no solid left over. We have less than the maximum amount. Once it reaches equilibrium, we could still get some more solid to dissolve. And so we won't see any solid in an unsaturated solution. If we do, that means it's not at equilibrium yet. All right, and then finally, we want to look at something that we refer to as a supersaturated solution.